Hey, sixth graders, this is Calibro Science coming at you from the West Coast. I got a call from a good friend last night. You may know him. His name is Albert. We're all going to be Feinstein. And he asked me if I would talk to you a little bit about waves, because that's what you guys are going over this week in science. And I said, of course, because he is one cool cat. Now, as a Cali boy, I've been shredding these gnarly waves since I was 5 years old. But before you can conquer these waves, you have to understand what they're all about. And we're going to watch a little video here to get you introduced to waves. And then I'm going to kick it back to my boy, Albert. We're all going to be Feinstein. He's going to take you through some gnarly labs. So here we go.
First things we need to know about waves is there are two different types of wave. One shown here by waves in the sea, and the other one shown by sound waves. So how are they different? Well, first let's look at the sea waves. If we look at them represented with this slinky, we see that the vibrations are at 90 degrees or perpendicular to the direction of travel of the wave. These are called transverse waves, and examples of them are waves in water, waves on a string, or light waves. Now let's look at the sound waves again. Again we see them represented by the slinky, but this time the direction of vibration is parallel to the direction of travel. These are called longitudinal waves, and the only example you really need to remember is sound. One really important thing to remember about waves is they only transfer energy from place to place, not any matter. And we can see that here by looking at a lovely rubber duck sat in a bath. As a wave goes through, the duck bobs up and down, but once the wave's gone, he's back to his original position. The wave has carried energy through, but it did not carry the duck with it. Finally, we need to know some key features of waves. First off, wavelength. A wavelength is the length of a full cycle of a wave, from one point to the next same point. It's easiest to think of as the distance from crest to crest, or from trough to trough. And we measure it in meters, and it's given the symbol lambda, a nice Greek symbol. The amplitude is like the size of a wave. But we need to remember that it's measured from the equilibrium position, or the central line, to the crest, not from the crest to the trough. Finally, frequency, which is the number of complete waves to pass a point every second. And it's given the unit of hertz. So an example of this would be if 10 waves pass in 2 seconds, the frequency would be 5 hertz. Using these things, we can actually now calculate the speed of a wave using the equation speed equals frequency times wavelength, or to give it in symbol form, V equals F lambda. So there's a lot to learn here, but once you've learned these core concepts, it will give you much more confidence in the rest of the topic.
Very cool stuff there, very cool. Like I said, I'm going to switch it over to my boy, Albert. We're all going to be Feinstein. You guys are going to go through some labs. Sixth graders, you stay cool. You hang loose, all my dudes and dudettes. This is Cali Boy Science. I'm out. All right, sixth graders. Albert here. I'm back. Let's get rolling on our Gizmo lab on waves. So, again, on Schoology, there is a tutorial on how to get logged into your Gizmo account. Okay, things still aren't working. Contact me. We'll get everything worked out. Okay. We also need our Waves Gizmo packet out on one tab. Okay, and this video out on another. Okay, sixth graders. Starting with our lab packet, we will be going over the prior knowledge questions along with the Gizmo warm-up. So starting with the vocabulary, we have amplitude, compression, crest, frequency, linear mass density, longitudinal wave, medium, period, power, rarefaction, transverse wave, trough, wave, wavelength, and wave speed. Now, I understand that that is a lot of vocabulary coming at you really fast, but hopefully a lot of those words will make a lot more sense by the end of this lab. Okay, our prior knowledge questions. 1. A buoy is anchored to the ocean floor. A large wave approaches the buoy. How will the buoy move as the wave goes by? And you need to make a prediction. This is a buoy right here. Okay, there's a wave coming by across the ocean. How is this buoy going to move as the wave gets to the buoy? Number 2. The two images show side views of ocean waves. How are the two sets of waves different? Here we have one set of waves. Here we have another. Okay, how are these two waves different? All right, our Gizmo warm-up. Ocean swells are an example of waves. In the waves gizmo, you will observe wave motion on a model of a spring. The hand can move the spring up and down or back and forth. To begin, check that the type of wave is transverse, the amplitude is 20 centimeters, the frequency is 0.75 hertz, the tension is set to 3 newtons, and density is 1 kilogram per meter. Let's hop on over to our wave and can make sure this is such. So, we have a transverse wave, right down here. Our amplitude is 20 centimeters, absolutely. Our frequency is 0.75 hertz, and our density is 1 kilogram per meter. We are good to go. Number 1, click play. How would you describe the motion of a transverse wave? All right, so here we have the motion of a transverse wave. How would you describe that? Okay, how would you describe the motion of this wave right here? Number 2, click pause. Notice the crests, the high points, and the troughs, the low points of the wave. Hey, here we have the high points, right here and right here. And those are the crests of this wave. The troughs are the low points of a wave. The low point of this wave would be right here. Reel number 2, click reset. Hit the reset button right there. Choose the longitudinal wave. And increase the amplitude to 20 centimeters. All right, we have our amplitude, we have it set to 20 centimeters. Click play. How would you describe the motion of a longitudinal wave? How would we describe the motion of this wave? Click pause. Notice the compressions in the wave where the coil of the spring model are close together and the rarefactions where the coils are spread apart. Okay, so our compressions would be right in here. See how these lines in the spring are all very close together? That would be an example of a compression. A rarefaction is where the coils are nice and spread apart, like right over here. Okay, 6th graders, that concludes our video. As always, feel free to hit the like button, smash that subscribe button. This is Albert. We're all going to be Feinstein. You stay classy, Stewartville.